Good evening, everybody. Let us begin today's session. So, in this week, uh, the sir has covered some very important things, which are smart pointers and concurrency. So, these are very useful features for real-world programming. So, I am going to explain both of these things. Okay. So, first let me say that what is a smart pointer. Okay, uh, we'll go over the slides, but let me explain it in my way first. So what we know is that in C we had a raw pointer, which is, let us say, int star p. Okay, this kind of a raw pointer we had. This usually points to some dynamically allocated object. Okay, so this might point to some dynamically allocated object like this, new int new int 50. So now the problem with this is that oftentimes programmers might forget to release this memory. Okay, or not only forget, what might happen is that during a exception, okay, the release code may not be executed. So what will happen is that there will be a memory leak. Okay, so since the memory is not released, it will be taken up by the program, and the program will continue to retain that memory although it is not doing anything. And if this kind of a code runs in a loop, okay, then every time the loop runs, it will take up more and more memory, and then after a point of time the program will crash because there is no more memory available in the system. Okay, so smart pointers are a uh, smart pointers are a way to automatically release memory basically. So you know that, so see, this is a dynamically allocated memory, so this allocation happens in the heap. Okay, now let us say that we are using a normal variable. Let us say we are using a normal variable. Okay, this allocation is done in the stack. Okay, this allocation is done on the stack of the OS, and as we know that the stack is cleared when things go out of scope. Let us say that we are in a scope block. Okay, this might be some function, or it might be a for loop, something like that. We know that when the program reaches here, then the stack is emptied. Okay, so everything that was over here, it is emptied. So this prevents a memory leak because this prevents a memory leak in case of stack variables, because the deletion automatically happens whenever things go out of scope. Okay, so smart pointers are a way to mimic this behavior. Okay, with pointers, that whenever the pointer goes out of scope, it should be released. Okay, that is the feature. So there is a very simple way we can create our own smart pointer, which is that we can do something like this, that uh, class my pointer. Okay, and then here let us say we are creating an integer pointer. We can have a int star p, and then in the constructor we can take my ptr, int star q, and then p, we assign q to p. Okay, so now this is fine. Okay, now the genius thing is this, that we can create a destructor, and inside the destructor we can write delete p. Okay, so now let us say in our code we use this smart pointer. Okay, so we are using the smart pointer in our code. So then what will happen is that when we create this object, then the pointer will be passed into the constructor over here, and it will be stored here. But when we get to the end of the scope, this object will be deleted. This smart pointer object will be deleted. And why will it be deleted? Because it is in the stack. Okay, the smart pointer object itself is in the stack, but it contains something which is stored in the heap. Okay, so this this is stored in the stack only, whereas this is the variable which it's pointing to, it's stored in the heap. But what will happen is that when it goes to the end of the scope, uh, this my pointer object will be deleted because it's in the stack. But as soon as it's deleted, it will call the destructor, which will free up the heap memory also. So this is a way to mimic this automatic deletion mechanism for heap variables also, for dynamically allocated variables also. And like I feel that in C++ we need not use raw pointers. Okay, in most cases we can use smart pointers as also do our work. Okay, so now we'll go over the slide. Wait a minute. Wait a minute. Wait a minute. So this slide, uh, send the link. Oh, okay. This is search slide only. You can find it from the tutorials. I mean the lecture material section. So this slide discusses the pitfalls of raw pointers. Okay, because it says that it needs manual resource management. Then this slide discusses the operations that raw pointers have to support. So this slide discusses some pitfalls of raw pointers. So the first one is the assign problem. Okay, so suppose we have my class star p equal to new class. So p stores a pointer to this dynamically created object. Okay, but then let us say I assign p equals to 0. Then what will happen is the object which was created, it is now lost. Okay, there is no way to refer back to it. So but it is not destroyed either. So there is a memory leak. Then there is a ownership issue that suppose I I create a new class and I store it to p, and then I assign q to p also. and now let us say I call delete on Q and P. Then uh, since both the pointers point to the same object, the object is deleted twice. So I mean there is double deletion. So in the first deletion, so after the first deletion, that pointer now points to nothing. Okay, it's a meaningless pointer. Hello. Okay, so it's a meaningless pointer. But the second deletion is also called. Okay, so this is there. Then it says that to solve this we have to use exception handling through try catch. So we'll have to write a lot of try catch or a lot of conditional statements to handle these things. You can see here that it says that like this complicates the code a lot because there are lots of exceptions and we have to write code to handle all of them. So sometimes we can get by using references instead of pointers, and they might be preferred in some cases because it avoids some problems of pointers. Next we come to the smart pointers. So a smart pointer is a C++ object which stores which points to dynamically allocated heap objects. Okay, and it supports operations like this. Okay, construction, destruction, copy assignment, dereferencing. Then all these benefits are discussed. So this is the basic interface for a smart pointer. Okay, so obviously it will be a templated class because the underlying pointer might be of any class. Okay, so we'll have a constructor. Okay, and we have a constructor. We will also have a copy constructor. We'll have assignment function, and then we'll have a destructor. Okay, this is the main thing, the destructor. It ensures that when the smart pointer goes out of scope, the pointer is also freed. Then we have the dereferencing operators also. Then here it's discussed how smart pointers operate. Now we come to the policies. Okay, so uh, we okay, so the policies and the smartness of this pointer. So first one is that it always points either to a valid object or it is null. Okay, and it deletes the object once there is no more references to it, and preferably there should be no overhead. uh, okay, so it should be thread safe, it should be exception safe, and it should not have problems with circular references. Okay, so now this is a key topic. Okay, there might be so regarding smart pointers we might have storage policy, ownership policy, conversion policy, and null test policy, and depending on all this there might be different flavors of smart pointers. Okay, okay, so this is an important part. So when we come to ownership policy, so there are two kinds of pointers. One is the std unique pointer and one is a std shared pointer. So a unique pointer has exclusive ownership of the pointee. Okay, which means that there can be no other smart pointer which points to the same pointee. Okay, and then we have shared ownership. where the ownership of the pointer is shared between smart pointers. Under this we have two classes, std shared pointer and std weak pointer. So what will happen is that suppose I have a unique pointer, okay, and I assign another pointer to it, okay. So suppose I have a unique pointer and I now suppose I have a unique pointer p and I set q equal to p, which means I am copying p into q. Then what will happen is that it will transfer the ownership of copy, which means that it's a destructive copy. So it means that when p is set to q, then p will get the ownership of the object, and the original variable p, it will become null, okay. So this is a destructive copy. As you can see how it works. Suppose we have this copy constructed, then we set our pointy equal to the sources pointy, and we set sources pointy equal to 0. So we are removing ownership from the source. So this is a interesting effect, okay. It's called the maelstrom effect. So suppose we have a function which accepts a smart pointer by value, then what will happen is that when we call the function, a copy will be performed and the ownership will be transferred to the local variable inside the function. But after the function then finishes, then the smart pointer will also be destroyed, right? So there is no way to get back the smart pointer, okay. So it says that we should always pass smart pointers by reference, okay. So these are some advantages of smart pointers. Next we come to shared pointers. So in shared pointers, multiple pointers multiple pointers, they refer to the same object, okay. So how it's done is that it is counted, okay. The number of references to the pointer are counted. So suppose one smart pointer is pointing to something, then another smart pointer also points to the same thing, then there will be a count inside the class which will be incremented. And then when some pointer releases the pointy or it's destroyed, then the count will be decremented, and when the count becomes 0, then the pointer is freed, okay. So you can see multiple or single raw pointers per pointy with count in free store, and it count is a member of the object, and destroy the pointy object when the count equals 0. Now we go to the next module. So this is a recap slides. Next we come to the ownership policy. So there might be a situation when A holds a smart pointer to object B and B holds a smart pointer to A, and this forms a cyclic reference. So this is cyclic references may go undetected, and both the objects may remain allocated forever, because one object is referring to another and the other one is also referring to it. So both the objects are being referred to, so they cannot be deleted. Okay, so this is a problem. So here the solution is presented for this. Okay, let me explain this here. So the problem is this. Okay, so suppose we have a object A. So as we know that smart pointers, they deallocate. Wait, it's not visible, right? Okay, as we know that smart pointers, they release the object which they are holding when the count approaches zero. Okay, so suppose there is an object and nothing is pointing to it. Okay, there is no pointer which is point. There is no reference to the object. Then the smart pointer will free up this object. So the problem is that there might be circular references. Okay, what might happen is that A might refer to B, and then B might refer back to A. Okay, so in this case, since both the objects are being referred to, so then uh, both of them will stay in memory forever, and it will not auto delete. Okay, nothing will auto delete. Even if, let us say, we want to deallocate both of them. Okay, but that won't work because there will be references to each individual object, so it won't be deleted. So the solution is that we create two kinds of pointers. One is uh, the normal shared pointer, and the other one is the a weak pointer. Okay, so the weak pointer, we create a weak pointer like this, which is just used to refer to that object. Okay, but it is like there will be, so this is just used to create the data structure. Okay, but it will not take part in this uh, counting and deallocation and all these things. So that is the solution. So in effect, what is happening is that A is referring to B. Like if we are counting references, then A is referring to B, but B is not referring back to A. Okay, so this is, so because this is a strong link and this is a weak link. Okay, now let us continue. So this slide says that how, why like allowing implicit conversion might be problematic. Okay, because the smart point, if we allow implicit conversion, then the smart pointer might get automatically converted to a raw pointer, which will defeat the purpose of the pointer only. So that is why in the standard library no conversion is allowed, and we have to use this get function to obtain the raw pointer. Next we come to the null test policy. So we can test whether a smart pointer is null or not using these methods, because the standard library provides this function for uh, to convert the smart pointer into a boolean object. Okay, so all these three tests will work. So these are the different kinds of pointers, which is unique pointer, shared pointer, weak pointer, and auto pointer. So unique pointer you saw. Okay, then we have shared pointer, which you also know that multiple pointers can point to the same thing. Then weak pointer is also a shared pointer, but it is a weak reference. Okay, it is not used, like it is somewhat like shared pointer, but it is not used when keeping count of the number of references. So then there are examples. Okay, I will skip over this. Then we'll go to concurrency. So this is a basic example of a thread. Okay, let me show. Let me explain in the slide. So now we are beginning concurrency. Okay, so concurrency means that we want to do the same thing in parallel. Okay, so we want to parallelize the code. Suppose we have some code like suppose we have some task where we have a array, and there are many numbers in the array, and we want to find its sum. Okay, so what we can do is that we can split up the array into uh, 10 parts. Okay, let us say we split it up into 10 parts. So in this case, let us say we split it up into 5 parts. Okay, then we can give each part to a separate computer. Okay, separate computer or processor. Okay, we are giving each part to a separate computer or processor, and each computer returns a sum. Then we can add up all the sums together to get the final sum. Okay, so this is the basic idea behind concurrency, that we want to divide a repetitive task into multiple subtasks, and we want to give each subtask to a separate computer or a separate processor, and then each processor will handle the subtask, and then their results will be combined back to produce the final result. Okay, so this is the basic thing about concurrency. I mean the basic meaning of concurrency. Now in C++, how is concurrency done? We have a function. Okay, what we usually do is we create a function. Okay, we create a function, and then from some place, okay, from main or some other place, we create a thread. Okay, we create a thread and we pass this function as the argument. Then what happens is that this this function is executed parallelly to the rest of the code. Okay, so suppose we have this main code. The main code will go line by line, right, from the first line to the last line. But suppose we put a thread here. We put this function over here. So then let us say normally what will happen. Normally suppose we had called the function in the main, then it would execute line by line, then it would go to the function, it would execute the function line by line, and it would then return back. Okay, so the main code would pause while the function is executing. Okay, but in this case what will happen is that this thread will be executed parallelly to the main code. Okay, so your main code will be running and parallelly the function will also be running. Okay, and this parallel execution will be handled by the CPU. So because of this, this is how concurrency is done in C++, and because of this there might be various problems. For example, a simple problem might be this, that your function might take a long time to complete. Let us say it takes 10 seconds to complete, and let us say your main function only takes 1 second to complete. So what might happen is that when you let us first say we do it normally without the thread, then your main function is executing, it will call the function which will take 10 seconds, and then it will come back to the main and it will finish the rest of the main. So it will take total 11 seconds to complete. Now let us say we use the thread and we run the function in another thread. Then what will happen is that the function will take 10 seconds to run and the main will also will take 10 seconds to run, and both will happen parallelly. But what will happen is that the main will finish early, much early, because it will finish 9 seconds early than the function. Now since it has finished, it will then quit the program. So your function won't do anything useful because your main has finished working. So the program has quit. Okay. So these kinds of problems might arise due to concurrency. Therefore, it is very crucial that we program things properly when we are using concurrency. Okay. So here an example is shown. We have a function here. Okay. We have a function here. We have two functions actually, and then we write. Then we create two threads with each of these functions. We have two functions and then we create two threads with each of these functions, and they will execute parallelly to the main, but they are more heavier than the main function because they involve printing a string to the console, whereas the main function has no other statements. So the main function will finish working before small f and capital F finish. Okay, so this is this is how to use thread, but this will not work. So then what we have to do is we have to wait, we have to instruct the CPU to wait for the threads to complete. Okay, and that is done using the join command. So we create the two threads here, and then we write t1 dot join and t2 dot join. So this means that when the main is executing, it will wait for t1 to finish. So it will wait for the function small f to finish working, then it will wait for the function capital F to finish working. Uh, so when it's done, okay, then only the main function will exit. So it means that the joins ensure that we don't terminate until the threads are completed. But you can see, since they are working in parallel, the output might be non-deterministic as it's shown here. This is an example of how we can pass parameters to the thread. For that we have to use std bind, okay, and you can use it as shown here, std bind and then f and then my vector, okay. It will basically, it will take this function and it will create a new function which has no arguments. So you can see in the normal call, okay, when we pass the function, it has no arguments, okay. But suppose we have to give an argument, then we can use std bind. It will take this function f, okay. This function f, it accepts the vector of integers. So it will take this function, it will take your argument and it will create a new function which has no arguments and it will pass it to thread. So this is how it works, okay. So this shows an example of how we can get an output from the thread. We have to modify the function such that it accepts the pointer, okay. You have to modify the function such that it accepts a pointer, and then we can pass this, we can bind the function, the argument and the output return value, and we can pass it to thread, okay. Then it will give the output in that pointed variable. So this is the, okay, somebody is asking that can you share the link of the PPT. So this is search PPT only, okay. You can find it in the lecture material. If you go to this week's if you go to this week's content, you can find it in the lecture material. Okay, now I will come to a important topic, which is race condition and data race, okay. This is a very important topic because of which there are some mechanisms like locks and mutexes to counter it. So a race condition could be when two threads are accessing the same, they're writing to the same resource. Sorry. So a race condition can happen when two threads are reading and writing from the same resource at the same time, okay. So suppose we have a database, okay. We have a database and then we have two threads which are accessing the same same database at the same time. Then let us say that one of the threads, it has some computation to do, so it reads the database, it does some it does some calculation and then it stores the answer back. Okay, and now thread B also has the same task to do as thread A. Okay, so thread A and thread B are doing the same task. Okay, they are reading some value from the database and they're modifying it and then they're writing it back. Okay, now what might happen is that thread A reads the value. Okay, so the reading part is done for thread A and it is now modifying the value. So then meanwhile B also reads the value from the database. Okay, but note that B will read the old value. Okay, because A is still modifying and it has not finished. So if I do thread A and B's history like this, we can see that, let us say first thread A reads the database. Okay, it thread A reads the database. Then now thread A is modifying it. Okay, thread A is modifying it, but it has not finished modifying because let us say it takes some time. Meanwhile, what happens is that since both are happening parallelly, B also reads the database. Okay, and B also starts modifying. Now let us say that A has finished modifying and it writes back the updated value to the database. So uh, write back the updated value. Okay, now after this B has also finished, so B also writes back the updated value. Updated. Okay, so suppose that since both the tasks are happening together, let us say that this is the execution order. Okay, let us say by chance it happens like this. So you can see the problem here. The problem here is that A is reading the database and it is updating it. Okay, and but B B is reading the old data. Okay, it should read the new data, right? Because see, A has started first. Okay, A has started first. Uh, suppose this thing was happening in a non-concurrent scenario. Let us say it was happening one by one. Then what would happen is that A would read and write, and then B would read and write. They are happening one after another over here. So then B would read the updated value. Okay, it would read the updated value. But in this case, what is happening is that B is reading the old value. Okay, it is not reading the updated value because the updated value has not been calculated yet. And then so A is doing all this, and then B is modifying and writing the value which is based on the old data and not the new data. So in a way some information is lost over here. Okay, or the database might become inconsistent. So this is an example of a race condition, and we have to, even when we are doing concurrent things, sometimes we have to schedule things a little bit. Okay, we have to specify the order of execution a little bit to make sure that these kinds of things don't happen. Like we should we should not read and write at the same time. Okay, a shared resource. In the example, okay, in the example in the slide, the professor has given an example where we are calculating sum of squares. So we are calculating 1 square plus 2 square plus 3 square, okay, dot 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 plus n square. So in each thread we are creating n threads. Okay, we are creating n threads, and each thread is calculating I cross I. So it is squaring I. Okay, it takes one number and it squares it, and then it adds the value to the sum. Okay, then it's doing sum plus equal to I into I. Now this might not work properly because while one thread is updating the sum, another thread might also be updating the sum. Okay, so it will create an uh, inconsistency in the program, okay, and because of which the actual output might be lesser than the correct output, okay. So as you know, 1 square plus 2 square to n square, this is equal to n plus 1 2n plus 1 by 6, okay. But when we do this in a concurrent manner, the sum of the sum returned by the program might be lesser than this, okay, because it will miss some of the additions. So to prevent that, we have to ensure that only one thread is modifying the sum at the same time, okay. Since sum is a shared variable between the threads, we have to make sure that only one thread is modifying it at a single time. And there are various mechanisms to do it, such as locks, mutexes, then semaphores. Okay, so we'll study these now. Okay, excuse me, thank you for waiting. So here there is an example of a race condition. So we are calculating this summation of I squared, okay, and we are using this program to do it, where we have a square, we have accumulator, and then we have a function called square, and we are doing accumulator plus equal to x into x, and then we are writing a for loop I equal to 1, I less than equal to 20, and square I. Okay, so this is a single threaded program, as you can see, and it will give the correct result. Now let us write a multi-threaded program to do the same thing. Okay, so we'll spawn 20 threads for the 20 numbers, and then we'll join the results in the accumulator. So this is how you convert it into a threaded program. The this part remains the same. Then we create a vector of threads, and we fill the array like this. Okay, we create a thread with the function, okay, and the argument, which is I. Okay, square and I. So this is the function and this is the argument. So this is how we create the thread, and then we wait for all the threads to join, because if we don't wait, then the main function will finish its computation and exit. Okay, so now it says that it might like in this case it might by chance work. Okay, so what we'll do is that we'll introduce some random delays into the function. Okay, we'll modify the square function such that there is some random delay between each thread, because if we are doing a heavy task, there might be a random delay and it might be unpredictable. Okay, so this is a good approximation of a real world heavy computation. So when we do this, okay, when we do this, okay, so it says that we'll suddenly get on some particular run, we'll get a different answer. Okay, uh, okay, so you can see that when we run the program again and again, okay, sometimes it might give a different answer. As I said, that the sum produced by this program might be lesser than the actual sum. The actual sum is 2870, and the sums which are produced might be lesser than this. Okay, it might be lesser than this because of the race conditions. So this statement, okay, accumulator plus equal to x into x, it can be split into three statements actually, because see, this is a shorthand for writing a instruction. Okay, but this is not a atomic instruction. Atomic instruction is a instruction which cannot be broken up. Okay, in the CPU itself, it is executed as one instruction, so it cannot be broken up. But this or operator, okay, accumulator plus equal to x into x, this line, it is not one instruction in the CPU. Okay, it is actually three instructions, which is the multiplication and then the addition. So there might be two threads which are interleaved like this, and it will produce an accumulator which is 4 instead of 5, because there the reading and writing is happening at the same time. Okay, so now there we'll discuss two solutions to mitigate this problem. One is the mutex and one is the atomic solution. Okay, they will prevent this by allowing only one thread to access the shared variable at a time. Okay. See, a mutex allows us to encapsulate blocks of code that should be only executed in one thread at a time. So in the main thread, what we do is we before this. So see in the above thread, okay, the shared variable is the accumulator, okay, because the accumulator is accessed and modified by every thread, okay. So that is the shared variable. So before this accumulator, we create a lock, okay, accumulator mutex dot lock, and after the modification, we write accumulator mutex dot unlock. Because of this mutex, what will happen is that there are 20 threads, right, but only one thread will be able to be inside the mutex at a time, okay. So if suppose thread number 5 it gets the mutex lock, and now let us say thread number 7 also wants to get the mutex lock, it will not be given and it will have to wait until the mutex is unlocked. So it will wait until thread number 5 finishes and unlocks the mutex, only then thread number 7 will get the mutex, okay. So we create these changes in the previous code to uh, incorporate the mutex. And so that is about mutex. Now we'll see the atomic, okay. So C++11 has introduced a new container which is an atomic container. So basically atomic container is a container which can only be accessed or modified by one thread at a time, okay. So it will not support multiple threads reading or writing to it at the same time, okay. So we create a atomic and then we specify the data type and we initialize it with 0. Then we can write our code as normally we write, okay. We do not need to use mutex and all. We can write it as we normally write. And since it is atomic, one of the threads will have to pause until the other one finishes execution. So to incorporate atomic, we have to just include these two lines, okay, nothing more. This is the same slide, okay. Let us do the exercises now, okay. So this is the first question, okay. Please try it on your own. I will give a couple of minutes, okay. Yeah, Anubha, the link to the slides that contain the questions, okay. So you can access it from the course website, okay. But I will share the link here also. But today's slide is not uploaded yet, okay. I will upload it after the session. Okay, now let us solve this question. So uh, in this program we have a struct which has a data member which is a list of integers, and it has a pointer to a variable integer pointer called as result. Then we have a constructor which takes a list of integers and the result, and it assigns these data members. Then we are overloading the call operator, okay. So this object then becomes a functor, okay. This object actually becomes a functor because we are overloading the call operator. And then in the call operator we are basically multiplying all the elements of the list, okay. We are multiplying it as shown. Then we have another function which prints an integer list, okay. Then we create the main function where we have an integer list like this, and we create a result variable. Then we have to call this function in a thread. You have to call this function in a thread which is t, and then we are waiting for the thread to join t dot join. Otherwise, the main function will exit, okay. And then I call this print function with the integer list, okay, and I print the result. So now it says that fill in the blank at line 1 with appropriate options such that the output becomes, okay, this is wrong, it should be 10, 10, 20, 30, 10, 20, 30, and 6000. So basically I will print the list, and okay, sorry, wait, it was correct only. It was correct only. The output should become 000 and 6000. Now you can see if you look at the main function, so the last variable to be printed is res, which means that res should be 6000. And now res is basically the product of all the array elements. So you can see that 10 into 20 into 30 would give 6000. Okay, and you can also see over here that the for loop is also setting the array elements to 0. So after this thread executes, the contents of the list will be 000. So it will match with the output. So basically we have to just call this functor, okay. We have to construct the functor and we have to call it, okay. Nothing else. So when we initialize a thread, we have to pass a callable object, either a function or a functor, okay. So so this should be a callable object, okay. In our case it will be a functor and we'll have to construct the functor. So all of these are constructors here and you have to choose one of them. So the last one, okay, which is a std bind and product, and then this, okay, this will not work because it will bind the constructed, okay, and it will not, I mean, I think it will probably even give an error because std bind, it works with callable objects, whereas this product is a class. Okay, this product is a class, so I don't know how it will work. But for the other three, if we look at the first one, in the first one we are calling the constructor of product with a, this ampersand will give a pointer. Okay, so we are calling the constructor of product with a pointer to the list and a pointer to the result. Now this will not work because the constructor accepts a reference to the list. Okay, so it accepts a reference, and the output should be stored in a pointer. So this will not work. D is also not working. Your B and C will work because in B we are calling the constructor with the list and the output variable, and in C we are giving it a reference to a list and the output variable. So the B and C will work. A and D will not work. So the answer is B and C. Any questions? Okay, then I will proceed. This is the second question. Please try it on your own. This will be 120. Okay, let us proceed with this one. Okay, so here we have a function called print, which accepts three integers and a constant integer reference, and then it does some summations and subtractions. Then we have a main function, which has some variables, and it creates a function f using std bind. Okay, and it uses all this, and then we are calling this f function with three arguments. So okay, so then what will be the output here? So in your std bind, okay, wait a minute. So we are binding the print function with these arguments. Okay, so the print function accepts four arguments, and we are giving four arguments here. We are giving four arguments here. So from this we can see that your n1 will be equal to underscore 2, n2 will be equal to val, which is equal to 10, and this is passed by value, so it will not change also, and n3 equal to underscore 1, and n4 equal to ampersand val, which means that it will be a reference actually. N4 is a val, but it is a reference. Okay, it is a reference. So this is equal to 10, but it might change in future also. Okay, so here underscore 1 and underscore 2 means that the first argument and the second argument of the a bounded function, okay, f function respectively. So after this line we set val equal to minus 10, we set val equal to minus 10, and the significance of this is that we have a reference to the val. Okay, so now n4 will become minus 10. Okay, since we had a reference to the val, so when val changed, it will also change that value, and it will become minus 10. Then we are calling the f function with these arguments 100, 20 and minus 100. So our first argument is 100, so n3 will become, this will become 100, and our second argument is 20, which means that n1 will become 20. Then we can calculate the result based on this formula, which will be 20 minus 10 plus 100 minus 10. So the answer is minus 80. So therefore the answer is B. Okay, so so that is the answer of this question. Any questions? Okay, then let us continue. This is the next question. Please try on your own.
Sir, 7. Option C, 7.
The answer is 7. Okay, so here you can see that we have a function called step up, which does these computations. Basically, it takes the number of steps and it adds it to this value. Okay, it adds it to this val variable. So now the problem is that, as we saw, and then we are calling three threads with different arguments. Okay, and we are also waiting for them to join. Now the problem is that the as we saw, there might be a race condition. There might be a race condition because of which, depending on the order of interleaving and the order of execution of these threads, the output may vary. Okay, so as we all know that if we add 1, 2 and 3 to 1, okay, we get 7. Okay, so the actual answer should be 7. Actual answer should be 7, but due to race conditions, the answer that it produces can be lesser than 7. Okay, so that might be the case, but the thing is that here we are using a lock here. Okay, we are using std unique lock, uh, lock. Okay, so since we are using the lock, so then uh, since we are using the lock, so only one thread will be able to access the variable at a time. Okay, only one thread, so it will avoid the race condition and it will work correctly. Okay, so then the answer will be 1 plus 1 plus 2 plus 3 equal to 7. Okay, so that is it for the question. Okay, so any questions you might have?
Hello, hello.
Hello, yes.
Sir, why we use why is better than normal function?
What? What? I did not understand.
Sir, why we use concurrency like thread and all over normal function?
Okay, so we might use it because, so see, our processor, ours, there might be only one or two CPUs. Okay, in our processor. So for example, my laptop has 8 cores. Okay, my laptop has 8 cores. So you can think that it has 8 processors like this. Okay, it has 8 processors, but many times we want to run many tasks at once. Okay, for example, right now I am running Google Meet, I'm running PowerPoint, and I'm also recording the screen. Okay, so we might have to run many tasks simultaneously. So in that situation, we need concurrency. Okay, to do all these tasks simultaneously. Also, there are some tasks when, if they are if you can split them amongst all these cores, then it will run faster. uh, normally a program is done line by line like this. Okay, so suppose we have a long program, it will have to be done line by line. Okay, which means that it can only execute on one processor. Okay, because uh, if we are at this line, we cannot suddenly execute that line. Okay, we have to wait until all of the lines in between are executed. Okay, but there are some problems which can be split. Okay, so you can give it to the other cores and it will increase the speed of the processor. So if you use a single threaded program, it can only be run on one processor at a time, or a one core system. But let us say we are able to split this program. Okay, let us say hypothetically we are able to split this program. then what we can do is we can give this to one core and then we can give this to another core. So our program speed will theoretically double because they will execute simultaneously. Okay, they are on different chips, so they will execute simultaneously. So it will theoretically double. So that is why if there is any task that we can parallelize, okay, like for example summation or products, okay, these kinds of things, then we should parallelize them. Like we should split them and we should run them in different threads and give them to different processors. Okay, so that is why we use concurrency.
Thank you for answering.
Okay, now let us continue. Wait. Okay, this is the same question with a mutex. Okay, so please try.
Excuse me, sir.
Yes,
Sir, whether there will be an unproctored exam, sir?
I don't know actually. Like, I do not. I actually don't know because I don't.
Okay, sir. Sir, for other courses like Joy of Computing, like other courses, we had unproctored exams, sir. So like that, this course is having unproctored exam, sir.
I don't know. Okay.
Okay, sir.
Okay.
Okay. Okay, sir. Thank you, madam. Thank you.
So let me continue with this question. So here we are using a mutex to achieve the same effect. Okay, we are locking. We are calling mutex.lock and mutex.unlock, which means that this is a critical section. It means that only one thread can access this section at a time. Okay, two threads cannot simultaneously enter and execute in this section. Okay, so it should produce the same effect, and the answer should then be 7. But there is a problem here. We are writing we are declaring a variable int val, but we are also making it thread local. So thread local means that although this variable is written in the global scope, all of the threads will have their own individual copies. Okay, so let me write it here. All threads so all threads have their own copy of the variable. So this means that if we are creating three threads, they will have separate copies of val. And also note that your main function is also a thread. Okay, it is the default thread. So it will also have its own copy of val, which means that this val will not be the same as the val of the other threads. So so basically your this T1, T2, T3 threads, they will not interfere, or they will not modify this val, and so this val will remain 0 only. So that is why the answer will be 0. Okay, this will remain 0 only. Okay, so that is the answer of the question. So any question you might have? Okay, then let us continue. So this is the next question. It is a somewhat big question, so please try on your own.
Sir, option A.
Yes, yes. Excuse me, wait for a minute. So can you explain why it will be option A?
So do we have to unlock printer mutex in unit log? I just
No,
don't
no.
know.
And then I think it will be option A only, because we are calling the first thread with request copy 1 and 10, and then we are calling the second thread also with request copy 2 and 10. So it is going
The
into
struct will be global,
what?
so value will be changing. It will be in global scope, so value will change.
Okay, okay. So it will go into this function and it will increment it by 10, and also the scanner count by 10, and then this will increment it by 20 and also 20. So then the answer will be 1030 and 1030. Okay, so then it will be A. Let us go to the next question. Please try this question. Okay, so in this question, we have a function. Uh, called add to vec.
Sir, option C.
Yes, option C is correct. There is another option also. So we have this function add to vec that adds the numbers 3 and 4. Okay, there is a loop I equal to 3, I less than 5. So it adds the numbers 3 and 4 into this vector. And then in the main code we have a vector where we first add the numbers 1 and 2. So we have a loop I equal to 1, I less than 2. So it will add the numbers 1 and 2. Then we are spawning a thread where we are keeping this function, and the output variable is this vc. I mean, sorry, the input variable is vc, and then we are printing it. Okay, so note the order of execution here. First we are spawning the thread. So first we are spawning, then we are printing the vector contents, and then we are joining it. So what might happen is that before this new elements are added, the printing might take place. Okay, the printing code might execute before the new elements have been added, because the join comes after the printing. Okay, so you have to think of that while answering. So your option A, okay, it is actually a valid output because we are adding the numbers 1 and 2 to the vector, and then we are spawning the thread, and then we are printing it. Let us say that this add to vec function, it fails to execute by that time. Okay, it takes some more time to execute, so the numbers have not been added. So then the answer will be 1 and 2 only. So 1 and 2 is a valid output. Okay, then your 1 2 3 4 is also a valid output. This is the output that will happen when everything works normally. Okay, so you will have your vector will contain 1 and 2, and then you insert 3 and 4 to the vector, so you will have the output as 1 2 3 4, which is a valid output. So this is also not the answer. But for part C, this is not a valid output because your vector already has 1 and 2. So your vector has 1 and 2 before the thread spawns. Okay, so that order cannot change. Your 3 cannot come before 2 because it starts with 1 and 2. So C cannot be a valid output. So C is the answer. By that same logic, your D is also not a valid output because 1 and 2 should come in the beginning. Okay, it is coming at the end. So your D is also answer. So we have two answers for this, C and D. So any questions till now? Okay then. So actually I am not feeling well today, so I would like to conclude the session early today. Okay, so I'm concluding the session now. Okay, thank you for attending.
Thank you.